Welcome, friends. This lecture is on carbocation oblique carboniamine. First of all, I will talk about the nomenclature. I have written both carbocation, carboniamine. They are synonym. Yes, they were used as synonym. But a famous scientist, Ola, isolated a species CH5 plus pentavalent carbon, or I can say hypervalent. The valency is more than 4, that's why hypervalent. If you want to see this reference, this is given in Jerry H. March, Advanced Organic Chemistry by Jerry March. Earlier, carboniamine was very popular. Still, I see in many papers of MSc classes carboniamine, but nowadays it is not correct to say carboniamine after the identification of the CH5 species by a scientist, Ola. Ola was a scientist who did contributed a lot in carbocation, and there is a very old book of Ola on exclusively devoted to carbocation. Anyway, this is much more correct to spell carbocation than carboniamine. So right word we should use, that is carbocation. And I will talk about some books which you can refer. Jerry March is one of them. Mukherjee Singh reaction mechanism. Yes, that is a very beautiful example. In old edition, Mukherjee Singh was using carboniamine, but if you see the latest edition, they have rectified. Now they are also using the word carbocation, which must be used. So you can refer Jerry March, Mukherjee Singh, even Jagdamba Singh, and a separate book on reactive intermediates is also there. It is not harm to see Jagdamba Singh and Yadav, or Mukherjee Singh is an outstanding international level book, and Jerry March, there is no any question. What do you mean by carbocation? I am taking a simple example. This is tertiary butyl chloride, right? Tertiary butyl chloride. Suppose it ionizes, it will give this is one positive carbon having 3 methyl. This is nothing but tertiary butyl carbocation. Tertiary butyl carbocation, and obviously chloride ion will be there. This is an example of carbocation. I could took this example also. CH3Cl, that is theoretically, I am absolutely right. That is a trivalent carbon with positive charge. But practically, the formation of methyl carbocation never takes place. Always, if you see the SN2 reaction, methyl chloride undergo hydrolysis. By SN2 reaction, chloride ion leave from this place and hydroxide ion attack from the opposite. That is a concerted reaction. But theoretically, yes, it may be possible. This is a perfect example. Tertiary butyl carbocation and chloride ion. How we can define the carbocation? This carbon I am looking trivalent, positive charge is there, and if I calculate the electron, 2 plus 2 plus 2, 6 electron. So such type of species of carbon which is positively charged, always carbocation is positively charged. There are 6 electrons in the outermost shell. 2 plus 2 plus 2, 6 electrons. So carbocation, positive charge carbon is there. 6 electron in the outermost shell. Number 3, that is a trivalent species. You will always found carbocation trivalent species, and whenever trivalent species is there, that is a planar in structure. So remember, carbocation is always planar in structure because that is sp2 hybridized. 3 sp2 hybrid orbital will arrange in a planar structure. How many electrons? 6 electrons. Electron deficient species. It should have 8 electrons, but it is having 6. Highly electron deficient species, or I can say it is a Lewis acid. It will accept the electron from any electron donating species, so that is the Lewis acid. So what is the definition? Such type of species in which positive charge carbon is there, right? There are 6 electrons in the outermost shell of carbon. Carbon is trivalent, right? When trivalent carbon is there, that is sp2 hybrid, planar in structure, highly electron deficient species, because instead of 8 it is having 6 electrons, and because it is highly electron deficient, so that is Lewis acid will accept the electrons immediately from any donating species. And what I did say, I took the example of tertiary butyl chloride preferentially because tertiary butyl carbocation formation takes place. Theoretically, it was nothing wrong if I took the example of methyl chloride that was dissociated into methyl carbocation and chloride. But that practically never happens because such high unstable methyl carbocation will be that it will always prefer the concerted reaction. Now I come to classification of carbocation, how we can classify the carbocation. Classification of carbocations, right? We can classify carbocations in 3 categories: primary or 1 degree, secondary or 2 degree, tertiary or 3 degree. Yes, we can classify the carbocations in 3 categories: primary, secondary, tertiary. Primary is also known as 1 degree, secondary is also known as 2 degree, tertiary is also known as 3 degree. What do you mean by primary carbocation? Such type of cation or carbocation in which positive charge lies on primary or 1 degree carbon atom. Yes, such type of carbocation in which positive charge is present on primary or 1 degree carbon. As I took the theoretical example, this is methyl carbocation. That never formation takes place practically, but theoretically, I can say this will come under the category of carbocation 1 degree because this has only 1 carbon. Then you see CH3, CH2. This is ethyl carbocation. CH3, CH2, CH2. That is N-propyl carbocation. N-propyl carbocation. I take this example, isobutyl. Yes, isobutyl. The positive charge is present on 1 degree. That is isobutyl. I take example CH2 double bond CH, CH2 plus. That is allyl carbocation. Allyl carbocation. I take example C6H5 CH2. That is benzyl. That is benzyl carbocation. Because positive charge is present on 1 degree carbon. Some students might be confused. What is 1 degree carbon? Whenever 1 carbon, that is always 1 degree. This is 1 degree because this is attached to only 1 carbon. This is 1 degree carbon because it is attached to only one carbon. This is isobutyl 1 degree because this positively charged carbon is attached to only one carbon. Allyl carbocation, positively charged carbon is attached to only one carbon. Come to benzyl C6H5CH2 plus, this positive charge carbon is attached to one carbon. So whenever positive charge lies on 1 degree or primary carbon, that is known as primary carbocation or 1 degree carbocation. And what do you mean by primary or 1 degree carbon? Such carbon which is attached to only one carbon atom. I think these examples are enough to understand what is 1 degree or primary carbocation. Now I come to second category, that is secondary. But generally we write SEC dot, secondary carbocation. Carbocation. What do you mean by secondary carbocation? Such carbocation in which positive charge is present on the carbon which is attached to two carbon atom. Earlier we saw the example methyl, ethyl, normal propyl, isobutyl, benzyl. Positive charge carbon was attached to only one carbon. Secondary means the positive charge carbon should be attached to two carbon. The first example of 1 degree carbocation was methyl carbocation, which I did say practically not possible. But in secondary, you cannot have 1 or 2 carbon example because the positive carbon should attach to 2 carbon atom. So you see, this is positive charge carbon attached to 2 carbon of methyl group. This is first member, I should say, isopropyl carbocation. This is a 2 degree carbocation or secondary carbocation because positive charge lies on 2 degree or secondary. I take example another secondary butyl. This is a very interesting example. I will come to this example at the time of stability. This is secondary butyl, right? One side methyl, one side ethyl, means positive carbon is attached to 2 carbon. Now I would like to say, I did write isopropyl, secondary butyl, fantastic. But in this case, we can take the second nomenclature for carbocation, second nomenclature. What is that second nomenclature? Suppose CH3, we count all the carbocations as the derivatives of methyl carbocation, right? So this carbocation, I did say isopropyl, this is also known as dimethyl carbocation. Please understand, no confusion must be there. That is isopropyl, everybody must know. But second nomenclature, on plus charge carbon, there are 2 methyl group. So I can say 2 hydrogen of methyl carbocation are replaced by methyl group. So that is methyl carbocation also. Right, friends? What? This is secondary butyl. What will be the another name? One side ethyl. So I will write ethyl, methyl. But don't leave here. Methyl carbocation. The parent carbocation was methyl. So I have to write methyl carbocation. Any other example of 2 degree carbocation? This is C6H5. This is C6H5. This is CH. This is CH. What is this? Diphenyl. 2 hydrogens are replaced by phenyl group. Diphenyl methyl carbocation. Diphenyl methyl, sorry, There should be methyl, otherwise that will wrong. Methyl is already there. Diphenyl methyl carbocation. So either isopropyl, secondary butyl, or diphenyl methyl. You are looking the positive charge on a carbon which is attached to two other carbon. These are example of secondary or 2-degree carbocations, right? Now I come to third degree. We have seen 1 degree such carbocation in which positive charge carbon is attached to one carbon only. Secondary or 2 degree in which positive charge carbon is attached to two carbon. Third category, tertiary or 3 degree. Such carbocation in which positive charge lies on tertiary carbon. This is positive charge carbon, this is a tertiary carbon. Or the positive charge carbon is attached to at least 3 carbon atom. This is known as tertiary category or 3 degree carbocation. And I did took the example. This is nothing but tertiary butyl carbocation, right? According to second nomenclature, if this is the derivative of methyl, 3 hydrogen of methyl carbocations are replaced by methyl group. So this is trimethyl carbocation, right? Suppose I take this example, CH3, CH2, C, CH3, CH3. This is nothing but tertiary pentyl carbocation. Now there are 5 carbon, 1, 2, 3, 4, 5. That was tertiary butyl, but this is also tertiary because positive carbon is attached to 3 carbon atom. So this is tertiary pentyl. 5 carbons are there. What could be the another name? 1 ethyl. So I will write ethyl, 2 methyl. So dimethyl, ethyl, dimethyl, methyl carbocation, right? Ethyl dimethyl methyl carbocation. I think this nomenclature should be quite clear. If all the 3 hydrogen of methyl carbocations are substituted by methyl, that is tertiary butyl or trimethyl methyl. If 3 hydrogens are replaced, 1 by ethyl and 2 by methyl, ethyl dimethyl methyl carbocation, or also known as tertiary pentyl carbocation. Another example I will take of tertiary carbocation, that is a very interesting example from stability order, that is C6H5. This is C6H5. This is plus charge. What is this? Triphenyl methyl carbocation. You cannot give it a second name, that is only known as triphenyl methyl carbocation. Triphenyl methyl carbocation. So I would like to repeat it again. We can classify carbocation in 3 categories: 1 degree, 2 degree, 3 degree. Primary, secondary, tertiary. Primary carbocation, which are attached, in which positive charge carbon is attached to one carbon only. Example: methyl carbocation, ethyl carbocation, normal propyl carbocation, isobutyl carbocation, or benzyl carbocation. Secondary or 2 degree, when positive charge carbon in carbocation is attached to 2 carbon at least. Isopropyl, right? Also known as dimethyl. Secondary butyl, also known as ethyl methyl carbocation. Third category, in which positive charge lies on 3 degree or tertiary carbon atom. This is triphenyl methyl carbocation. Obviously, we are looking the positive charge on the 3-degree carbon. This is ethyl dimethyl methyl carbocation. This is also tertiary. Earlier, I took more example, that is trimethyl. Suppose instead of ethyl, the third is also, that is trimethyl methyl carbocation or tertiary butyl carbocation. I think it should be clear. And if any doubt is there for lower classes, BSc classes, I would like to remove by explaining what you mean by 1 degree, 2 degree, 3 degree carbon and 1 degree, 2 degree, 3 degree hydrogen. I take only one example so that there should not be any confusion. I take an example, I just take carbon skeleton. This is carbon skeleton. Right? Suppose I have to reply from this side. This carbon, this is attached to only one, this is 1 degree. This carbon is attached to 3 carbon, 1, 2, 3, 3 degree. This carbon is attached to 1, 2, 3, 4, 4 degree. This carbon is attached to only 2 carbon, 2 degree. This carbon is attached to 4 carbon, 4 degree, and this is again 1 degree. So now you can understand. The carbon which is attached to only 1 carbon, that is 1 degree. Carbon which is attached to 2 carbon, that is 2 degree. Carbon attached to 3 carbon, 3 degree, and carbon attached to 4 carbon, that is 4 degree. And suppose the hydrogen which is attached to 1 degree, that is 1 degree hydrogen, attached to 2 degree, 2 degree hydrogen, attached to 3 degree, 3 degree hydrogen, and attached to 4 degree, that will be 4 degree hydrogen? No, never. Because 4 degree means this carbon is attached to 4 carbon, no scope of hydrogen, carbon is determinant. So carbon might be of 4 type, primary, secondary, tertiary, quaternary, right? Primary, secondary, tertiary, quaternary, but hydrogen will be of 3 type, primary, secondary, and tertiary. Is it clear? Now I will go further about how we can explain the stability of carbocation. Stability of carbocations. Rather, before coming to that, I should explain in brief which are the factors which influence the stability of carbocation. First is inductive effect. Inductive effect. Second is hyperconjugation. Hyperconjugation. Third, resonance effect. Resonance effect. Please take into consideration permanently the stability of carbocation are explained with the 3 factors: inductive effect, hyperconjugation, and resonance. If some of my old students are listening the lecture and if they do remember a little bit, I always started before carbocation these 3 effects in very detail when I talk to even MSc part 1 or previous classes. Because if you know all these 3 effects, you can understand the stability. Now, because there is a limitation of time, I will explain with a little bit elaborately, but I will not take separately. Suppose I take tertiary butyl or trimethyl carbocation, right? I take CH3, CH plus, CH2, CH3. I take CH3, CH, then I come to theoretically, practically not possible, they are never formed, so unstable. ethyl and methyl ion. What is inductive effect? Inductive effect means permanent displacement of electron towards more electronegative atom or a group. The replacement, that is always permanent. Inductive effect is always permanent. Permanent displacement of electron towards more electronegative group. If I tell you to remember all alkyls, that generally I was telling all alkyls are plus I, right? Oxide is plus I. They will always repel the electron, they will never attract. Except oxide and these alkyl groups, all groups, sulfonic, nitro, chloro, bromo, iodo, hydroxo, all are minus I effect. But alkyl have plus I. Minus I means to attract the electron towards itself, and plus I means to repel the electron to another side. So if you see tertiary, there are three alkyl groups, three methyl group, all will see repel the electron towards positive carbon. So the magnitude of the positive carbon will decrease. Magnitude of positive carbon or positivity, I should say, will decrease. Due to presence of 3-methyl group, alkyl group, and due to plus I effect, there is decrease in the magnitude of the charge. That's why tertiary butyl is more stable, undoubtedly. These are two very confusing carbocations, I am telling you. If you see the inductive effect, you can say very easily methyl, ethyl. The alkyl group, they always have plus I effect, plus inductive effect. As the size of alkyl increases, methyl least, then ethyl, then propyl, etc. As the size of the alkyl group will increase, the plus I effect will also increase. You are looking one methyl, one ethyl. According to inductive effect, it should be more stable than isopropyl because there are two methyl groups. In this case, most stable tertiary butyl out of these, most stable means what I have written right now. Tertiary butyl most stable, then ethyl methyl carbocation less stable, then tertiary because there are two groups, but one is methyl and other is ethyl. That should be more stable than isopropyl or dimethyl methyl, and that should be more stable than ethyl because methyl is smaller, and the least stable, that is methyl. So how we can explain with the inductive effect? Inductive effect is the permanent displacement of electron towards more electronegative atom or a group, right? There are two types of effect, plus I, minus I. Plus inductive effect means such type of groups which repel the electron far away. They will not attract towards themselves, they will repel, like alkyl group, repelling towards positive carbon, repelling towards positive carbon. So whenever plus I alkyl, plus I effect, alkyl group is there, alkyl group always increase the stability of the carbocation. More number of alkyl group, more will be the stability because magnitude of the positive charge will decrease. So tertiary butyl, secondary butyl, isopropyl, ethyl, methyl. This is, I should say, not practically possible. Second effect is hyperconjugation. Hyperconjugation, how we can explain? Hyperconjugation. Second effect, first was inductive. That is also known as no-bond resonance. Such type of resonance in which no bond will remain with the remaining species. No bond resonance. I take the example of ethyl, first of all. Right? This is positive charge. Undoubtedly, this is ethyl carbocation. Ethyl carbocation. Now, what happens in hyperconjugation? You see, sigma electron will participate. This, any of the three bond, one by one will come to this place, and the second hyperconjugated structure will be H, C, H plus C, H, double bond C, H. See carefully. In hyperconjugation, sigma electrons participate. Out of these three, every sigma bond will participate one by one. This is one of the hyperconjugative structure. Why I did say no bond resonance? This H plus, this is very much attached to this. This H plus doesn't have any bond with the remaining species. So please mind it, hyperconjugative structures are counted by the number of the hydrogen present on the alpha carbon of the positive charge. Suppose this is positive charge, this will be alpha carbon, there are 3 hydrogen, I can say there will be 3 hyperconjugative structures. 3 hyperconjugative structures. Right, friends? Now I take the example of isopropyl. How hyperconjugation will take place in isopropyl? That is a 2 degree or secondary. This is alpha carbon, this is alpha carbon. The carbon adjacent to the positive charge or directly attached to positive charge gets alpha. So, what will happen? Any hydrogen will come. Suppose I have taken this one. The second hyperconjugate structure will be, I will keep these 3 hydrogen right now as such. Then C, this I can say H, this is double bond, this is H, this is H, and this is H plus. Right? This is hyperconjugative structure. In this hyperconjugative structure, this hydrogen participated, this might be participate, this might be participate, and all these 3 will be participate. How many hyperconjugative structure you expect? 6 plus 1, I can say 7 hyperconjugative structure. Hyperconjugative structure. Or better we say 6 plus 1, that will be nice. 1 is original and 6 hydrogen will participate. Total 6 plus 1 hyperconjugate. If you take tertiary butyl carbocation, similarly, this is tertiary butyl carbocation, this is alpha carbon, this is alpha, this is alpha. How many alpha carbon? 3 plus 3 plus 3, 9. These 3, these 3, these 3. All 9 hydrogen will participate and there will be 9 hyperconjugative structures. So remember, what is hyperconjugation? What is happening in hyperconjugation? This positive charge, which was confined to one atom only, now that is delocalized among 6 hydrogen atoms. In tertiary butyl, this positive charge, which was localized to one, in hyperconjugation, that has been delocalized to 9 hydrogen atoms. In chemistry, more localized any charges, less stable will be the species bearing, less localized any charges, more stable will be the species bearing. यदि चार्ज delocalized हो सकता है, स्टेबिलिटी ज्यादा होगी. Why benzene is stable? Due to resonance, there is delocalization of pi electron. So this is no bond resonance, but in benzene there is resonance. In no bond resonance, the H plus and remaining species doesn't have any band. That's why this is not known as no bond resonance. But alpha carbon, remember, in hyperconjugation, only hydrogen of alpha carbon. In the case of ethyl, only 3 hydrogen were there because one alpha carbon was having